All right, so we have seen the application of the projection theorem for general vector spaces and a small example on the function spaces where we ended up with the Fourier series representation. Now we will consider the case of n-dimensional complex vector space, okay? And here we will consider our vector space Cn, so it is n-dimensional complex vectors, and let M1 to Mk be a basis for a subspace M of the Cn. All right. That is M is equal to span M1 to M2 Mk. And what we would like to do is that given an arbitrary vector in Cn, we would like to find the point in our subspace that is close to that X over there. And so we know that we can write this X vector as a decomposition of X onto our subspace and so on orthogonal complement. And we also know that by the projection theorem that X1 and X2 are unique. This decomposition was also unique. And we are trying to find this X1 vector which is close to X that within the subspace, which can be expressed as a linear combination of the basis vectors in that subspace. Okay. And we will start by defining that B matrix over here, which is whose columns are that we will put the basis vector, given basis vectors as the columns. Okay. Let me try to write down these things so that it can be more visualized. So consider that a B matrix, okay, which is composed of these vectors as in the columns 3 and mk over there. Okay, so if I multiply that B matrix by the coefficients alpha 1, alpha 2, and alpha k, that multiplication will be equal to this. Each of these coefficients will multiply those columns and sum them up. So that will be simply equal to summation I from 1 to k alpha I and I. So then what we are looking for is this was the expression for our optimal solution x1. So I will express x1 as b times alpha, and I will try to find this alpha if I'm given that B matrix over there. Okay, this is also written here. Anyways, so we will consider the standard inner product in Cn as the inner product of two vectors, two complex vectors, is equal to y conjugate transpose times x. So this is conjugate transpose operation. In some textbooks, it is shown by this H, this Hermitian operation. Sometimes it's shown by star. Sometimes something else. Anyways, and if we have the real vectors, so if we are talking about Rn, n-dimensional real vectors, this inner product will be equal to y transpose x because the conjugate of real vectors will be equal to themselves. All right, so we were given x and we were looking for this x1, which is in this form of b times alpha and b times alpha, according to this definition. And what we will exploit is basically the projection theorem, which states that the error is perpendicular to the, once again, sorry about this, why do I do subspace? Okay, subspace. Managed to write it correct, sorry about that. Okay, so the error will be simply equal to the x minus b times alpha, which was this was x1 if you remember, and that will be perpendicular to the vectors mi for I is equal to 1 to k over there. And so we will write the equations for this inner product x minus b alpha and mi is equal to 0 for I from 1 to okay, and if I write down those inner products by using this standard definition, so I will complex conjugate transpose of mi times x minus bi, so that inner product is equal to mi conjugate transpose times x minus b alpha, and that should be equal to 0. And for I is equal to 1 to k. And notice that if I write this down for different I values, for example, n1 conjugate transpose times x minus b alpha should be equal to 0, m2 conjugate transpose x minus b alpha should be equal to 0, and mk conjugate transpose x minus b alpha should be equal to 0. And I can write down these equations in compact form as follows, if you agree. So I can write that thing as B conjugate transpose times x minus B alpha equals to 0. Okay. Why? Because this, if you look at this B conjugate transpose matrix, so we defined the B matrix where the columns are these basis vectors, and B conjugate transpose will be something like this, right? You get all these columns transposed in as the rows over there. So if the first column is M1 of B, the first row of B conjugate transpose will be M1 conjugate transpose. And if the second column of B is equal to M2, the second row will be M2 conjugate transpose. Okay. And since we're in the, if this is n by k matrix, this will be k by m matrix, okay? Because the length of these vectors will be n in the n-dimension space. All right, so that will simplify things a bit. So I will continue from this equation from there on. So this equation states that, okay, I can go scroll down. Okay. So from there I can write B conjugate transpose X is equal to B conjugate B times alpha. Okay. And here I will this was a K by N matrix. Okay. And this was a M by K matrix. So their multiplication will be K by K matrix. Okay. And from the uniqueness of this x1s and alpha, that will be also invertible, but I will write it down first, okay? So E conjugate transpose times B is a K by K matrix. And the x1 is unique. The projection of the x vector onto our subspace is unique, and the composition is unique, so alpha i's are also unique. Are unique because it's a unique representation with linearly independent vectors. Then this equation, let's say if this equation is, sorry about that. And this equation has a unique solution. Okay. Equation above. Has a unique solution. And if this is a if this equation has a unique solution, then B conjugate B should be invertible, and B conjugate B is a full column rank matrix, and it is invertible. So then I can write these unknown alphas as alpha is equal to B conjugate transpose B inverse times B conjugate transpose X. And if you remember, x1 was equal to B times alpha. So x1 was equal to B times alpha. And the projection of x onto our subspace, which is equal to x1, is equal to B times B conjugate transpose B inverse times B conjugate transpose X. So I will define this factor in front of that X, which is a matrix, as a P matrix, okay? And this is an orthogonal projection matrix. This is an orthogonal projection matrix, okay? Which projects X onto our subspace M. So in summary, at first we were given a basis set which is composed of linearly independent vectors for our subspace M, which is composed of these vectors m1, m2, and mk. So we constructed a B matrix where we put the columns to be equal to the basis vectors themselves. And then we can express the linear combination of these basis vectors as B times alpha, like that, okay? And then we try to find the optimal alpha, which gives the projection of the given point onto our subspace M. And we write down the equations for the error being perpendicular to the subspace itself. So we wrote down this x minus b alpha with inner product with mi should be equal to 0 for all these i's. And then this ended up in a compact form where we ended up using this B conjugate transpose matrix, so that we were able to find the projection of the given vector x onto our subspace by a matrix multiplication. Okay, and that matrix multiplication is done by using an orthogonal projection matrix, and when you multiply a given vector with that matrix, that projects the given vector x onto our subspace M. Okay, so this is a special matrix. So I would like to also give you one more remark. So notice that. So it said that our x is sorry. So we said that x can be decomposed into the subspace and its orthogonal complement like that. Okay. So this is in M and this is in M orthogonal complement. And we can find this x1 on our subspace by multiplying the x vector by this P matrix over there. Okay. And so x is equal to P times x plus x2. Okay. Then from there, I can say that x2 is actually is equal to identity matrix minus P times X. Okay. And this is the now I do have now another projection matrix which projects the given vector X onto M orthogonal complement. So maybe we can write it down explicitly. This is another projection matrix. And it projects X onto M orthogonal complements. So for the orthogonal projection matrices, we have the following properties. So since it was defined as the B conjugate, B inverse B conjugate, so their conjugate transpose is equal to itself. Okay, so P conjugate transpose is equal to P, and if you're talking about the real matrices, then it is symmetric. Okay, so this has to be a symmetric for real projection matrices. Okay.
Hocam,
Yes, please.
pi için şey de dememiz gerekmiyor mu? Sadece reel kontantlardan oluşuyor.
Yok, hayır. P conjugate, hani burada da zaten şey var ya, elemanlar var burada hani, yani conjugate transpozlarda. P
Anladım,
conjugate
tamam.
transpose P'ye eşit oluyor yani. Kompleks olabilir. And another property is that the P square is equal to P. Okay. And so we can check that by writing down these equations, right? So let me try to write down. Or there's also another interpretation that I would like to share with you. So P squared can be written as P times P, and that will be equal to P times, where was it, the expression? So, okay, B times B conjugate transpose B inverse times B conjugate transpose, that's P, and I'm writing B once again as B times B transpose B inverse times B conjugate transpose. And notice that, so for example, multiplication of these two will be equal to identity, and that will be equal to the P itself, B times B conjugate transpose B inverse B conjugate transpose, which is equal to P. And notice that if you take the higher powers, P square, P cube, that will be the same as well, right? So you can either, there's also a reason for that, right? So, because notice that if P squared is equal to P itself, okay, and if it is equal to P to the power I, then Px is equal to P squared times X, and that's also equal to P times X. It goes like that. And the reason is as follows. So let's go to our projection theorem picture. Where is it? Okay, somewhere over here. All right, so in the very last example, we talk about that. Okay, if we are given a basis set for our subspace M, So in previous cases, we were trying to find this M star, that x1, by doing different like inversions, Grammy matrices, inner products, etc. Okay, and in the last example, we were given, we were talking about this Cn, this n-dimensional vector space of n-dimensional complex vectors, and we were given a basis set that spans our subspace over there, right? So we were trying to find this x1 approximation, best approximation in M, and we were able to show that you can find that x1 by using a projection matrix. Okay, so we showed that x1 can be found for that n-dimensional complex spaces by matrix multiplication, p times x. So if you get this x vector over here, then you get this x1 as p times x. Belki morda falan yazayım da karışmasın. So here, so for this Cn example, we had x1 is equal to pi times x. So you can find the projection by simple matrix multiplication over there. So if you take a vector, and that P matrix projects any vector given x onto the subspace, all right? And I would like to ask you, okay, so what happens if I project a vector that lies within, which already lies within that subspace, and if I'm trying to find its orthogonal projection onto that subspace? So that will be equal to the vector itself, right? So it is almost like that. If the projection of a vector onto a line, if that vector is already on that line, will be equal to the vector itself, right? So therefore, so once you find px, which will be x1 over here, if you multiply it once again with the p matrix, which is the projection matrix, then it will be equal to the vector itself. So that is also equal to p square x as well, which is the p times px. So since px is already in M, the projection of that vector of that vector onto subspace M will be the vector itself, right? And so it has a, and if you multiply it by many times, it's not going to change the result, right? So you can multiply p to the power n x1 is still going to be equal to p times x. Because this projection matrix projects the vectors onto the subspace M already, and it doesn't change the vectors that is already on M. Or you can see it by applying the definition already. So p square is going to be equal to p itself, because we have this inverses multiplication results in the identity matrix in the middle. But it has intuitive meaning that, so the projection of a vector which lies onto the subspace, and projection of the vector onto subspace of the vectors that lies on that subspace is the vectors themselves. Okay. So that's the reason. Do you have any questions?
Hocam çok küçük bir şey soracağım da şu yukarıda x1'ler unique olduğu için alfa i'lara unique dedik değil mi?
Doğrudur. Hı hı. Yani aslında şöyle x1 unique. Alfa i'ler da zaten şeydi, hani şu vektörlerin bir lineer kombinasyonu bu x1'ı veriyordu. Hani bu vektörler linear independent'sa o şeyde nedir o? O representation da unique olmuş oluyordu. And representation of a ordered basis is unique. X1 is unique, o da decomposition unique'ti ondan dolayı. Yani x1 vektör alfa i'lerse aslında şu basis'e göre, daha doğrusu şu basis'e göre representation'lar aslında, değil mi? Representation'lar da unique'ti. Bir de şu x1'ın kendisi de unique'ti. Orada aslında iki şey bir arada kullandık. Güzel soru. Şu pekare meselesini anlatabildim mi? Mesela hani sanki iki kere üst üste project edemezsin. Zaten ilk projection sonunda subspace'in içinde kalıyor project ettiğin şey. Sonra da hani herhangi bir vektörü M subspace'ine project eden bir matrisle hali hazırda M subspace'inde olan bir vektörü çarparsan o vektörün kendisi çıkıyor zaten. Başka bir şey çıkmıyor yani. Yani o neydi bu P matrisi? Biz neyi buluyordu? Verilen vektörde P çarpı X M subspace'indeki en yakın noktayı buluyordu. Verilen vektör M subspace'in içerisindeyse ona en yakın nokta ne olmuş olacak? Kendisi olmuş olacak zaten. O yüzden P kare X, P küp X hepsi Px'e eşit yani. Aynı subspace'in içerisindeki vektöre en yakın nokta kendisi olmuş oluyor. Anyway, so let's also see one example of that orthogonal projection. By the way, I should emphasize that, so please make sure that in the exam when you're trying to find the orthogonal projection matrix, try, if you find the projection matrix that is not symmetric, then for sure you made a mistake at a certain stage, okay? So please do check that in the midterms or exams or in the finals. If you're finding a projection matrix, it has to be symmetric, okay? All right, so in the next example, we are asked to find the orthogonal projection of the vector 1, 0, 0 onto the subspace spanned by those two vectors, 1, 1, 1 and 1 minus 1. So we start by constructing our B matrix, right? So our B matrix will be equal to, I will write these vectors into the columns. So it will be 1, 1, 1, 1 minus 1, 1. And since this is a real matrix, the B conjugate transpose is going to be equal to B transpose, and that will be equal to 1, 1, 1, 1 minus and 1. All right, so, and I need to, in order to find the P matrix, so P matrix was B times B conjugate transpose B inverse times B conjugate transpose. So I need to find the inverse of the multiplication of these two matrices, right? So let me write that thing down. So B transpose B is going to be equal to 1, 1, 1 times 1 minus 1, 1 times the B itself, 1, 1, 1 times 1 minus 1, 1. That will be equal to 3, will be equal to 1, that will be equal to 1, and that will be equal to 3 once again. And B transpose B inverse is going to be the 1 over determinant of B transpose B, 8 times 3 minus 1 minus 1. All right, so if we continue writing down B, so we need to compute B times B transpose B inverse times B transpose, which is equal to 1, 1, 1 times 1 minus 1, 1 times 1 over 8, 3 minus 1 minus 1, 3 times B transpose 1, 1, 1, minus 1, and 1. Okay, now I can scroll down. That will be equal to 1 over 8 times 1 times 1 minus 1, 1 times. It will be equal to 3 minus 1, 2, 4, minus 4, right? Minus 4 and 2. Okay, and that will be equal to 1 over 8 times. Some of those will be 4, some of those will be 0, 4, the difference is 0, difference is 8, 0, there's some will be equal to 4, 0, and 4, and that is equal to 1 over 2, 0, 1 over 2, 0, 1, 0, and 1 over 2, 0, 1 over 2. So now we found the P matrix. This is the projection matrix, which projects any vector x onto subspace M, span of 1, 1, 1, 1, minus 1, 1. So one good news is that, first of all, let's say notice that we found the symmetric matrix. Okay, so P transpose is equal to P, and you can also verify that P square is equal to P. Okay, and the projection of x, which is equal to 1, 0, 0 onto M, is P times x, which is equal to P times 1, 0, 0. That will be the first column, which is equal to 1 over 2, 0, 1 over 2. And notice that I minus P is also a projection matrix. And it projects the vectors onto M orthogonal complement. Okay? For M orthogonal complement. And you can find that as well. Do you have any questions?